So here we are continuing on in the Aldehydes and Ketones chapter, and in this we're doing a Claisen condensation, which is just like the aldol condensation, which we have drawn at the top part of the page here. And we've drawn it before in our notes in a previous part. But we can form the enolate of the compound with the alpha hydrogens, and then that enolate can add to the other carbonyl compound, just like drawn at the top of the page, which gives us this. And then we can reform the carbonyl, kicking out our excellent leaving group of the methoxide, or at least good leaving group of the methoxide, to give us here. And since we have the very acidic hydrogen there, we all know we really need to remove it to get to the enolate, and the answer to the problem really has to have a negative charge on that alpha carbon between the two carbonyls. So here we have, if we think about the most acidic hydrogens, the ones alpha to the carbonyls. So the one that's going to be the strongest pK, the lowest pK, is going to be this hydrogen here, because when we remove it, we can draw an enolate that can go to either carbonyl. So this will be most acidic. The second most acidic would be the one to the ketone, and then the third, the one to the ester. So if we take a beta carbonyl compound and add methoxide to it, what we end up doing is removing the alpha hydrogen to form the enolate, and then that enolate can go do an SN2 with methyllithium in this example, but any compound with a good leaving group, to put a methyl on there, we still have one acidic hydrogen, so we can remove it to give us the next enolate, and then that can do an SN2 on ethyl bromide, and that gives us the methyl and the ethyl between the two carbonyls. Then with hydroxide, we haven't done this yet, but we all know that hydroxide is a good nucleophile, so we can easily add hydroxide into the carbonyl to form this, just drawing out the end of the molecule. And then the methoxide could easily leave to form the carboxylic acid, which once it forms in base, we would remove the extra hydrogen, and what we would end up with is the aromatic ring with the carbonyl, negative charge on the acid, the ethyl and the methyl on the carbons between. And then if we take acid and heat to that, we're going to protonate the carbonyl. If we draw it out showing what we have, we can protonate the carboxylate, making, and I'm going to draw it a little differently so we can see what needs to happen. Oops. Added a carbon. So we get to this, and we can easily see well, maybe not easily, but we can see a cyclic transition state happening where the beta ketone grabs the hydrogen off of the carboxylic acid and gives us an enol along with CO2. So this is a decarboxylation where we lost carbon dioxide to form the enol, and then since we're still in acid, we could see this enol going to grab a hydrogen off of our acidic water to give us the protonated ketone, and then that could easily lose a hydrogen to water to give us a ketone with, sorry, I lost my ethyl and my methyl. So what we've ended up doing in this step, very easily alkylating the alpha carbon to our starting carbonyl up here. Well, here in part 18 we have the following diethyene, and the only hydrogens that are different are the two between the sulfurs. So if we add butyllithium to it, we deprotonate it, we can do an SN2 on that attacking ethyl iodide. And then with butyllithium again, we can remove that hydrogen to form the anion again. And then with methyl bromide, it can do an SN2 again to attack the methyl. And we have added a methyl and an ethyl onto the carbon between the sulfurs. And then with mercury, chloride, and water, we can remove the sulfurs, and we end up with the carbon of our carbonyl throughout this mechanism. This carbon ended up acting as a nucleophile, which in all of the mechanisms we've seen so far, the carbonyl carbon has always been the electrophile, so this gave us a chance to get it to react differently than it normally would. And the next one, if we add hydroxide, or we'll make it ethoxide so it's the same as the ester, but it's going to deprotonate our diethylmalonate. And then that can react with benzaldehyde to give us we have that. We can grab a hydrogen off of ethanol to protonate our beta hydroxy or beta alkoxy, and then once we're there, it's just a simple elimination to get to our answer. And in this, we can draw it either as an E2 or an E1CB, just like we have in the past. If we draw it as an E1CB, we pull off the hydrogen to form the enolate. And then this kicks out the hydroxide as our leaving group to give us our answer. here we have another reaction where hydroxide is going to pull off the hydrogen between, we'll make it ethoxide, between the two carbonyls. And I changed it to ethoxide just because if it was hydroxide, it could change the ester to the carboxylate and mess up the problem. And then that, as we learned earlier, can do a 1,4 addition into the carbonyl to get to lost a carbon. The enolate, and then the enolate we can send the electrons back down to get to the negative on the carbon. And then that can go grab a hydrogen off of our acid in the workup to get us to our answer. So down here we have some reactions. In the first one, we end up with the equivalent of acetone being on the end, and then the carbon from the formaldehyde being here, and then our nitrogen on the end. And we'll draw the mechanisms for these three on the next page. In the next one, we form the enamine. And the last one, the enamine, acts as a nucleophile to go attack the benzyl bromide to add the carbon on.